Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In the previous sessions, we were talking about analysis of time series, index numbers, statistical quality control and control charts. As part of the study of statistical quality control, we are deriving various formula for control charts. There are two types of control charts for variables and control charts for attributes. In the just previous session, we talked about control charts for variables, that is control chart for x bar and control chart for r bar. The objective of this session is to discuss about control charts for attributes. A formula recall is necessary before we step into study about control charts for attributes. So, in a nutshell, we studied UCL, upper control limit, and lower control limit LCL, and central line formula for x bar chart and r chart. Control chart for x bar chart, always whatever be the condition, whether mu and sigma is known or unknown, control line for central line for x bar chart is x bar bar, that is grand mean, and UCL of x bar if mu and sigma are not known in the case, and using range, UCL of x bar is x bar bar plus a2 into r bar, and LCL of x bar is equal to x bar bar minus a2 into r bar. This is upper control limits and lower control limits for x bar using range if mu and sigma are not known, and the control limits for r chart for x bar chart using S, this is using R. Similarly, UCL of x bar is equal to x bar bar plus a1 s bar, and LCL of x bar is equal to x bar bar minus a1 into s bar, this is using S. And also we discussed a control chart for R. If sigma is not known, whatever be the case, whether sigma is known or unknown, central line for R stands for always r bar, and then UCL of R is equal to d4 into r bar, and LCL of R is equal to d3 into r bar. Now, all these values a1, a2, d3, d4 are tabulated in the tabular column. Similarly, if sigma is known, this is the case if sigma is not known. Okay. So, UCL of R is equal to d2 sigma, and LCL of R is equal to d1 sigma. Now, we are going to talk about control charts for attributes. The formula recall is for control chart for variables. Now, there are two control charts for attributes: control chart for fraction defective P chart, or the number of defectives NP or D chart. Next, control chart for the number of defects per unit C chart, or it is called control chart for fraction defective P chart. So, there is a difference between defective and defect. Defective means when there is a defect, the item is called as defective, whereas the particular problem is called as defect. While dealing with attributes, a process will be adjudged in statistical control if all the samples or subgroups are assigned to have the same population proportion capital P. And if D is the number of defectives in a sample of size n, then the sample proportion defective is given by number of defectives by the total number of items, that is P is equal to D divided by n. Hence, D is a binomial variate with parameters n and p, because D is equal to np. Np stands for the mean of the binomial distribution, therefore, D is a binomial variate. Thus, we have E of P is equal to E of D divided by n is equal to 1 by n into E of D. This is equal to a population proportion P. Similarly, variance of P is equal to PQ by n. Thus, the 3 sigma control limits, 3 sigma control limit general formula for any chart is always expectation of the parameter plus or minus 3 times standard error of the parameter. The expectation of the parameter here is capital P plus or minus 3 times standard error of P, root of PQ by n. Now, ultimately we will be having values of capital P and n, but capital P will give you capital Q, because capital Q is equal to 1 minus capital P. Therefore, the 3 sigma limits will be capital P plus or minus A into root of PQ, where A values are already determined for specific values of n starting from n is equal to 2 to 25 and are tabulated in the tabular column standard table. Okay. So, A is equal to 3 divided by root n. Thus, when the standards are specified, case 1, when standards are specified, standards in the sense standard values of the population. When standards are specified, we have P dash is given, P dash is given or known value, known value of P. Then we have UCL of P is equal to P dash plus A into root of P dash into 1 minus P dash, and LCL of P is equal to P dash minus A into root of P dash into 1 minus P dash, and the central line for P is just P dash, population proportion. Okay. P dash stands for the population proportion. Next, case 2. Case 2, when the standard values are not specified, standards are not specified, then that is the population values are not known, then Di is the number of defectives in ith sample and Pi is the fraction defective, for ith sample, because there are going to be k samples, k is equal to 1, 2, 3 etc. So, ith sample particularly we have taken, and Di is equal to number of defectives and Pi is equal to fraction defective. So, what happens, the proportion of defectives will be summation Di divided by summation Ni, I is equal to 1 to k, similarly I is equal to 1 to k here. So, Di, as already discussed, D stands for n into P, therefore, summation I is equal to 1 to n, Ni into Pi divided by summation I is equal to 1 to k Ni. Okay. That is, there are going to be k samples, for each sample there will be a sample size and there will be a proportion of defectives, a fraction defective for each sample. Likewise, it is going to be calculated For example, I will just write here, this is first a sample 1, 2, 3 etc. I, and this is etc. up to k. For each sample there will be a size and there will be a fraction defective. Similarly, N2, P2, like that we are going to have Ni, Pi, and for the kth sample it is Nk, Pk. Okay, and this summation is taken, summation Ni into each term is multiplied, and then summation is taken, and the summation of all Ni's is going to be taken. So that gives you P bar. Okay, what we are going to do with this P bar? We have to write the formula for CL of P and then UCL of P and LCL of P when the standards are not specified. So we have E of P bar, expectation of P bar is equal to expectation of this summation Di by summation Ni, or it is expectation of summation Ni into Pi by summation Ni, where I is equal to 1 to k, and this is nothing but population proportion. So UCL of P bar is equal to it is going to be P bar plus A into root of P bar into 1 minus P bar. LCL of P bar is P bar minus A into root of P bar into 1 minus P bar. This is P bar value itself, and CL of P bar is P bar itself. UCL of P is equal to P bar, small p only, P bar plus A into root of P bar into 1 minus P bar. LCL of P is equal to P bar minus A into P bar into 1 minus P bar, and CL of P is just P bar. So far we discussed a control chart for the fraction defective, that is called a P chart, when standard values are known and standard values are not known. So this is the formula when standards are not known, and the formula when standards are known or are specified. This is the formula. UCL of P is P dash plus A into root of P dash into 1 minus P dash, the same thing with minus and just P dash. Next is D chart, that is control chart for number of defectives. If instead of P the sample proportion defective, if we use D the number of defectives in the samples, then the 3 sigma control limits for D chart are given by, again by the standard formula. This is expectation of D plus or minus 3 times standard error of D. Okay, so that is equal to NP plus or minus 3 into root of NP into 1 minus P. Okay, so when case 1, when standards are specified, in the sense when population values are known, then we have a UCL of D is equal to N P dash plus 3 times root of N P dash into 1 minus P dash, and LCL of D is equal to N P dash minus 3 times root of N P dash into 1 minus P dash. CL of D is equal to N P dash. This is the case when standards are specified, that is the population values are known. Next, case 2, when standards are not specified, that is when the population values are not known, not specified, then we have UCL of D is equal to N P bar plus 3 times root of N P bar into 1 minus P bar, and LCL of D is equal to N P bar minus 3 into root of N P bar into 1 minus P bar. So that we have CL of D is N P bar. Whether standards are known or not known, CL remains to be same, is N P bar. Okay. Now always any value is not taken to be negative. Suppose if your LCL value comes to be negative, it should be taken as 0 because negative value is not allowed for control charts. Now, we studied the control chart for a fraction defective and control chart for number of defectives. For control chart for a fraction defective is denoted by P and control chart for number of defective is denoted by D chart. Now, what do we interpret from these kind of charts? Interpretation of P chart is, from the P chart a process is judged to be in statistical quality control in the same way as is done in X bar and R charts. If all the sample points fall within the control limits without exhibiting any specific pattern, the process is ultimately said to be in control. In such a case, the observed variations in the fraction defective are attributed to the stable pattern of chance causes. In the case assignable causes are not present and the average fraction defective P bar is taken as the standard fraction defective capital P. Now, suppose if there are some points outside the UCL, then points outside the upper control line are termed as high spots. These suggest the deterioration in the quality and should be regularly reported to the production engineers. The reasons for such deterioration should possibly be known and removed if the details of the conditions under which data were collected were known of a particular interest, specified interest, and the importance is if there was any change of inspection and inspection standards, that should be considered and ultimately taken into account for the smooth functioning of the production. Suppose the points lie below LCL, they are called low spots. Such points represents a situation showing improvement in the product quality. At the same time, the points should not be negative. Suppose if the points are negative, then it should be taken as 0. So, the points represent situations showing improvement in the product quality. However, before taking this improvement for guaranteed, for assured, it should be investigated if there was any slackness in inspection or not. We should be very careful in doing the inspection. So, we talked about points lying above UCL as high spots and the complete production has to be taken into account with starting from the data collection, and the points lying below LCL were called as low spots and there we talked the inspection should be taken into consideration as careful inspection. And next, when a number of points, when there are among the sample numbers, when the number of points fall outside the control limits, a revised estimate of population parameter should be obtained by eliminating all the points that fall above UCL. It is assumed that the point that fall below LCL are not due to faulty inspection. So, the standard fraction defective capital P should be revised periodically in this way. Next, we work out an example in drawing the control chart for fraction defective and comment on the state of control of the process based on the chart drawn. The following are the figures of defective in 22 lots, each containing 2000 rubber belts. Draw a control chart for fraction defective and comment on the state of control of the process. So, 22 lots has been containing 22 lots are been taken into account and each lot consists of 2000 rubber belts. So, for example, this particular value 425 is actually the number of defectives of out of 2000 rubber belts, 425 are defective in first lot. Similarly, 430 is the number of defectives out of 2000 rubber belts in second lot. For example, we talked about 420, this 420 is the number of defectives out of 2000 in the last 22nd lot. Can you just check how many values are there? 6, so 11, 11 plus 11, 22 values are given. So, we have to draw control chart for fraction defective and comment on the control of the process. Here we have fixed the sample size. We have fixed sample size n is equal to 2000 for each lot. Ni is equal to 2000 for I is equal to 1, 2 etc. up to 22. If di and pi are respectively the number of defective and the sample proportion defective for ith lot, then we have according to the formula pi is equal to di by ni. Since ni is same for all, it is di by 2000 for I is equal to 1, 2 etc. up to 22 lots. Okay. And these are values given in the tabular column. A sample number is here the tabular column is divided into two parts for the first 11 items and then for the second 11 items, that is 22. So, sample number is 1, 2, 3 etc. up to 11 and then it continues as 12, 13, 14, 15 etc. up to 22. DI values as given in the question is 425, 430, 216, 341 like that up to 22 values it is 420. Now, this pi is 425 divided by 2000 is 0.2125. Okay. And similarly, this value is 430 by 2000 is 0.2150. Likewise, this value here also it is calculated 402 by 2000 is equal to 0.2010. Okay. And everything has to be taken into account for total. Since writing 22 values in only one column is not possible, the whole tabular column has been divided. Therefore, summation di is the total of starting from 425 to 420. So, since it is divided into two parts, just take 3543 plus 3476. 3543 plus 3476. Okay. And this is equal to 7019. Okay. And similarly, summation pi is equal to 1.7715 for this particular sample number starting from 1 to 11 and summation di value starting from 12 to 22 is 1.7380. So, summation pi values is 1.7715 plus 1.7380 is equal to 3.5095. Therefore, P bar is equal to summation pi by n, which is 3.5095 divided by 22. There are 22 samples, isn't it? Is equal to 0.1595. Okay. And Q bar is equal to 1 minus P bar is equal to 1 minus 0.1595 is equal to 0.8405. Next, the 3 sigma control limits. The 3 sigma control limits for P chart are given by P bar plus or minus 3 into root of P bar Q bar by n. Okay. And therefore, the values are 0.1595. So, accordingly UCL of P bar is plus value and LCL of P bar is minus value, isn't it? P bar plus 3 into root of P bar Q bar by n. So, 0.1595 plus 3 into root of 0.1595 into 0.8405 divided by 22, and this value comes to be equal to 0.1841. Similarly, LCL of P bar is 0.1595 minus 3 into root of 0.1595 into 0.8405 divided by n is 22, which is equal to 0.1345. 0.1349. Next, CL of P bar is P bar itself, which is 0.1595. Okay. After we computed UCLP as 0.1841 and LCLP 0.1349 and CL of P as 0.1595, we draw the control chart for P, and then we see that the sample points corresponding to the sample numbers 1, 2, 3, 5, 12, 13, 14, 15, 16, 17, 20, 21, 22. That is out of 22 values, 11 values fall outside the control limits. So, almost 50% of the values are out of the control lines. Therefore, we term the process is not regarded as statistical control. In this session, we talked about control charts for attributes after recalling the formulae for control charts for variables. Control charts for attributes are P chart, fraction defective chart, control chart for number of defectives, D chart was discussed. Also, control chart for C chart, that is number of defects, defective and defect makes a difference, that also was discussed. An illustration was done in this session to draw the control chart for fraction defective. So, we calculated a central line for P, UCL of P, LCL of P, and we saw in this problem there were 11 values lying outside the control limit, and we termed the process given in this illustration is not in statistical control. Based on the discussion in this session, the following question may be posed. Construct a control chart for proportion of defectives in the following data of 15 samples of 100 tubes drawn randomly from the output of the process that produces several thousand units daily. Okay. So, 15 samples have been drawn, each sample is consisting of 100 tubes. It means the data given is sample number 1 and number of defective tubes is 8. It means out of 100 tubes in sample number 1, 8 tubes are defective. Similarly, out of 100 tubes in sample number 2, 10 tubes are defective. So, likewise in sample number 15 out of 100 tubes, 9 tubes are defective. Thank you.